I'll be talking about Jana, which is work on a project on secure computation with differential privacy and some of its applications. And this is work that's being done as part of DARPA's Brandeis program. Adam and I were talking, and he said he definitely wanted to have some representation of DARPA's Brandeis program, since it's for those of you who aren't familiar with it, it's all about privacy. It's named for Brandeis, the Supreme Court Justice, who's well known for his talk about the right to privacy. And in fact, we have, as it turns out, not just me, but several other of the talks are actually from people like the next one after this, that are involved with the DARPA, the Brandeis program as well, as it turns out. And I'm not going to talk too much about the overall program and the structure of the program, although it'll come up a bit later in the talk. Our project is led by Galois, which is a small company in Portland, Oregon, with partners University of Bristol, Rutgers, and George Mason. The main people involved at those places, just to put names and faces, are here. And so I'm going to give a bit of an overview of Jana and then talk specifically about how it's led to some specific research directions or engineering directions in some cases in secure multi-party computation, order-revealing encryption, and differential privacy. I'll talk a bit about our application scenarios as well. So what Jana is designed to do is be a private data as a service platform. So data as a service has proved very popular and useful. So this is often using cloud computing, web-based interfaces, or other kinds of standard interfaces that let your data be hosted somewhere else, and you be able to carry out various kinds of operations on it, like SQL queries and other standard things. People like them because they're easy to use, they have these familiar interfaces, they're fast and reliable, having the so-called ACID properties for database services. And they usually have at least some attention to privacy and security, things like encrypting the data in transit, in some cases the data at rest, and even in some cases allowing for computation on encrypted data, for example, via order-revealing encryption in some actual commercial deployments. So the Jana is really about exploring the use as well as the advancement of state-of-the-art privacy tools and methods to develop a private data as a service platform, meaning a data as a service platform with stronger and more flexible kinds of privacy and security guarantees in there. And then coupled with the implementation and practical use cases, this has also been really useful as a way to kind of drive exploration of engineering issues, practical trade-offs, as well as new research. So this slide came from Dave Archer, who would probably do a better job of describing it than I will. The way I like to describe, so this is Alice over here who's using this data as a service platform. What I like to sort of describe this is to say that so you start with the goal that you want to be using off-the-shelf things like your database service, and that you want to do some secure multi-party computation, some differential privacy, and some other security things. And then to actually make that work, you need all these other pieces around them. How do you get the data in a way that's already encrypted, but that you can do stuff on it? How do you take queries and make them work with this? Dealing with the users in terms of policies. And so there's all these different pieces that have to interact with each other and be made to work. Even under the assumptions that we want here, that there are potentially adversaries of various kinds who have the capability of being throughout the system. So in terms of capabilities that we have in Jana, right now we have a generous subset of SQL. As I said, we've got these ACID properties in a database service, which can be an off-the-shelf relational database management system. For privacy, and I'm gonna kind of use privacy to mean the parts of security that deal with encryption in any way, so I'm not gonna really distinguish there. So in terms of privacy, then data in transit is protected using public key cryptography. Data at rest can be protected in various ways, including sort of random, meaning secure, fully secure encryption. But we also, to explore, what are the performance gains from using other methods, have searchable encryption or other kinds of deterministic encryption in there as well. And then we have privacy of the results. Yeah, oh, sorry, I skipped this. The computation itself can be done using a secure multi-party computation, or when chosen to do so, can be done actually in the relational database if you have the right kind of encryption for that. And then the results themselves have privacy protections through differential privacy applied if the policy says that it should be, and caveat if it's one of the cases that we've so far actually implemented and deployed, but theoretically, if policy says so, with the differential privacy being done inside of the secure multi-party computation, so that even the Jana platform itself isn't going to learn the non-privacy protected result. And so far in terms of performance, we can easily handle databases of tens of thousands of records, moving into about hundreds of thousands of records with queries that can run in seconds to hours. Of course, your mileage may vary even with those number of records, but looking to grow that and scale that is definitely part of our project. And in terms of deployment, as I said, we deploy it as a web service using the so-called RESTful API, and a Docker appliance is available for that as well. So the currently implemented set of SQL is these various select, protect, join, union, intersect, and accept queries with data of various types, and queries can be nested, as you could see from an example here. And the underlying primitives or mechanisms that we use for that privacy protection then, or at least the ones that I'm really going to focus on for this presentation. So we use speeds as the multi-party computation engine for the parts that are done in secure multi-party computation. And Nigel, who's on our team, of course, brings that expertise with him for that. We have, as I said, the possibility of using order-revealing encryption or other kinds of deterministic encryption to make some kinds of queries much faster. And in the differential privacy, to allow that to be done within the secure computation, we've been using distributed generation of geometric noise to develop the differential privacy noise along the lines of a Dwork et al. Paper from 2006. So I'm going to spend probably most of the talk time talking about how this has led us to look at particular research questions, or questions that are kind of in that interface, maybe at the moment, between research and deployment. So in terms of the secure multi-party computation, in order to bring the data in, so if you have this outside data provider that has a bunch of data, wants to import it in an encrypted way into the system so that the system never sees the clear text data, but also so that then that encrypted data can be manipulated in an efficient way within the multi-party computation, then you needed, if you did this, for instance, tried to do this with AES, you'd have very inefficient multi-party computation to do that. And so I'll talk a bit about how we looked at solving that problem. That's work of Nigel and others on MPC-friendly symmetric encryption. Another direction in the order-revealing or order-preserving encryption setting was looking at better understanding the privacy implications and potentially improving the outcome of those privacy implications using order-preserving encryption. And this is a line of work that several directions recently have been active, one including that I'll talk about, that David Cash, as well as Thomas Dubuisson, who's at Galois, so David Cash at Rutgers, Dubuisson at Galois, along with one of David's students, did on looking at attacking order-revealing encryption. And then they're also doing ongoing work to try and sort of more fully characterize the trade-offs and develop best possible solutions. Because again, one of the things we're looking at is to be able to use this platform to really sort of, see at least the performance and engineering implications of trying to make different things work with each other, and then complementing that also with analysis to understand the privacy and utility implications as well. And then the third one that I'll talk about as well briefly is sort of similarly to how typical ways of doing standard symmetric encryption led to the need to do operations that don't work so efficiently in this kind of speeds type of MPC, secret sharing based MPC. Similarly, many of the ways to generate noise for differential privacy don't lend themselves well to doing in this MPC-friendly way. And but in contrast, some of the ideas from that the Dwork et al. 2006 paper did. So I'll talk about that. So for the MPC-friendly symmetric encryption, the goal in this work, and this, as I said, was work, it was Grassi, Rechberger, Rotaru, Scholl, and Smart in CCS 2016. They wanted to look at developing symmetric encryption that's suitable for use in a secret sharing based MPC system such as SPDZ, and they specifically narrowed it down to focusing on pseudo-random functions, or PRF, from which you can build symmetric encryption systems. And so in particular, to do this efficiently, as I was alluding to before, you want the data, we're looking at MPC systems in which the data is shared in terms of being elements of a finite field, FP, of some large prime characteristic. This is how SPDZ does it. It's how many other MPC systems do it. And if you want to abstract them to not just look at SPDZ, but this more general class, this kind of representation enables efficient protocols to compute relatively complex functions like integer comparison, fixed point arithmetic, and linear programming, but in contrast is not so efficient at dealing with things like byte-oriented or word-oriented operations such as those in AES, which in fact were chosen because they are so well implementable in hardware as well as in most software systems. But if you kind of view the language of an MPC system as being a different kind of software system, that kind of operation does not naturally lend itself to efficient representation. So what they did in their work is look at 3 different candidate PRFs. The Naor-Reingold PRF from 1997, one based on the Legendre symbol from Dam, Hallgren, and Ip in 2003, and then a specialized block cipher that some of the co-authors of this work had designed for use in snarks that's called Mimic. And they did a bunch of experimentation to look at how these all perform in different situations in a distributed multi-party computation setting. And what they found is no one dominates in all situations, but in terms of throughput, Mimic is the best. It has the lowest pre-processing requirements in SPDZ in particular, which has a pre-processing stage to it, and is also the best for this scenario that I was mentioning that we use in Jana, where you want to have someone external to the MPC be able to import data in a way that's going to arrive encrypted and shared, or conversely decrypting back out. And so the outcome for Jana is that we've included Mimic in the Jana code base. The more general outcome, actually, so latency was one of the ways in which Mimic did not perform the best. And so depending on your particular application, you might choose Mimic, or you might prefer, actually, the Legendre symbol one performed well in some cases. So here's an example of some of the results of that implementation and comparison. And this is specifically looking just at the Mimic and Legendre versions and looking at them in 2 settings, one using off-the-record encryption and one in a parallelizable MAC setting. And as you can see here, so let's see. So the 2 mimic ones are here, and the two Legendre ones are up there. So you can see in terms of latency, the choice is going to depend on the number of blocks, but that there's a couple of good options to use. And in terms of throughput, so how many authentications per second you can do, you're going to, now you see the two mimic ones clearly dominating at the top here. And so again, if you care about throughput, the mimic one seems to be the choice to use, and that is what we chose in the end for Jana. So that's an example, and I'm not going into details, and there are considerably more on them on the work that that they did on sort of tuning these things and evaluating them. But to just give it as an example of how this kind of a platform and these kinds of questions, that we've looked at with Jana have led to these results that are sort of interesting in and of themselves. So they're driving research there. Similarly, in terms of better understanding of order-preserving encryption, so one of the things that we wanted to explore in Jana was the security of a full secure multi-party computation versus things like order-revealing encryption that make the computation much faster, but also the performance gains that can be gotten by giving up some security, but at the same time you want to make sure you're not going too far. And there's sort of theoretical reasons that order-revealing encryption is worrisome on its own, but to sort of better understand it in terms of the implications of the definition, and then also in terms of actual practical use and what happens. So that was a second area that led to new research, and I'll talk about a little bit. So order-preserving encryption, and I should say this is work, as I alluded to before, David Cash, Thomas Dubuisson at Galois, and Betel Dirac, who's now graduated, a student of David Cash. So this was actually, that particular team to be working on this very much came out of the fact that we had this Jana team already working together, and that they realized that they could sort of work together to answer the kinds of questions we were raising for ourselves. So order-preserving encryption is a symmetric encryption scheme that is deterministic and strictly increasing. That is something you would want to use because if you can tell from looking at your encryptions certain things about their order, you can do certain kinds of operations, things like range queries, very efficiently because you don't need to decrypt to do it or do some sort of complicated protocol. So that's sort of the reason that you might hope to do it. But of course, it's inherently less secure. And I should say order-revealing encryption is just a generalized form of OPE that you don't have to actually preserve the order, but there's some efficient way to tell, given two ciphertexts, what their relative order are. So it enables efficient computation of range queries even on the encrypted data. And and as I was saying, it's inherently less secure than standard encryption, in particular, clearly subject to chosen plaintext attacks, because you can if you can choose a plaintext, see its encryption, you can compare it to other encryptions to know where they lie. But nonetheless, there was this research approach that people were taking, and actually practical approach. There are implemented systems out there that use it, with the goal being to construct ORE schemes, order-revealing encryption schemes, that have the best possible security against passive attackers who can capture ciphertext but aren't allowed to, they don't have access to the encryption mechanism to do the chosen plaintext attacks. And so, as I mentioned, there's been lots of work, including, so the idea of order-preserving encryption went back to Agarwal et al. In 2004. Really?
No, sorry.
Okay, thank you.
I didn't mean to distract you. But.
That's all right. And then the earliest sort of more formal definitions to 2009, but there's been work since then. But the work that came out of our project was looking at some new security issues, in particular looking at attacks where prior attacks would attack a single column. Their work looked at attacks that apply to correlated columns and allow more information to be gleaned by the attacker. And what they showed is it was possible to attack the multiple columns together, even in the case that the individual columns weren't amenable to earlier kinds of attacks. And then also looking at ORE on non-uniform data, that was the first analysis of practical order revealing encryption when data is not uniform. And in particular, so there's sort of there's kind of three potential levels of security you'd hope for with ORE. There's the ideal security, which says you do allow this order to be revealed, but nothing else should be revealed. There's ones that allow explicit leakage that is defined, and you can worry about how much is revealed from that additional leakage. And then there are implementations which may or may not actually achieve as much security as their definition. And so some of the practical constructions that are leaky were shown to reveal far more information on real data than leaky data, and they explored that through some experiments on geolocation and timestamps, and concluded from this that there's a need to cryptanalyze the definitions and the models, not just, so these weren't about breaking the implementation by seeing that the implementation didn't actually meet the definition. It's actually sort of cases where the definition itself is revealing far more than you might think. And so I'm not going to go through this in detail, except to say that they did a case study, one of a couple, on California road intersections as well. There were others that I'm not going to talk about. So here's the clear text data with these data points that are road intersections in California. And these are the encryptions, which should already be a little bit worrisome, because it still looks an awful lot like California. And part of, so this is some of that is the correlations there. Like, so the latitude by itself, probably not so revealing. The longitude by itself, not so revealing. But looking at it in 2D and looking at them together still sort of shows that general California shape. And in particular, they show that if the bounding box of the clear text data is known, then you can guess the data 30% of the points within 50 kilometers. And then they also looked at the California data set in the case of one of these leaky versions of ORE, in particular one that leaks the most significant bit in which any two ciphertext, the clear text related to any two ciphertexts differ. And there's those 27-bit representations. And in that case, they were able to show by, if you had just done, so they did a guessing algorithm for each x, doing some work, replacing it with a 1 or 0, and seeing which one, just a very simple case, which one maximizes the total pairwise, minimizes the total pairwise distance. And they ran that as an attack with an inference algorithm on various data sets. And what they found is that even though, going to the third bullet first, even though the explicit leakage allowed by this most significant differing bit leakage didn't reveal any point to within 400 kilometers, which you might say sounds not so bad, that that by doing that attack that I said there, it guesses more than half the points to within 0.5 kilometers. So revealing much more information than it might sound like naively. So the conclusions of that part of the work: correlation causes information leakage even for ideal ORE. The leaky ORE may be much leakier than previously thought, or than it would seem. And so, I think well, I was going to say the jury's still out. Either the jury's still out or the jury has convicted ORE as guilty, would probably be the way to go, or a little more judicially. It really, there may be only very specific kinds of applications for which is suited. So avoiding cases where data may be correlated, being very clear about the implications of the leak, and not only that, that it still needs to, that potentially different primitives and different approaches should be looked at, but also anytime there's a definition that relies on some kind of non-standard leakage that may need this kind of cryptanalysis to better understand. So turning then to the third area, and this is one where I would say we haven't really, it's been just more of a implementation and integration effort so far, but I think there's a lot of room for new research and some difficult problems here. So the idea here, the goal would be to come up with this MPC-friendly differential privacy, so figuring out ways that differential privacy can be done for the kinds of things that are efficient in speeds. You could also look at other ways of finding MPC that's more friendly to differential privacy, but this is the direction we're mostly looking in, and it's really, there's sort of potentially at least two issues there, that one of which is that many of the ways of generating the noise or even deciding how to do the computation themselves use operations that aren't efficient, but of course also there's lots of things you might like to compute, like machine learning algorithms and optimization and linear algebra that also don't lend themselves well to this. So there's a lot of work to be done there. What we've done so far to have something implemented is looking at things like sums and counts and averages, which are very sort of differential privacy friendly. We've looked at doing the noise in this geometric distribution way that approximate Laplace noise, and as I said, is similar to the Dwork et al. Paper. And but even so this picture, without talking through it in too much detail, is showing that if you do your differential privacy, your query without differential privacy, your performance is around 325 seconds, and that's just the secure multi-party computation of doing such a query. As you add more and more noise, so you have to flip more coins and do more of this distributed generation to get those numbers, it is starting to, it does add a significant performance penalty. So that's something that needs to be addressed. Lots of questions around privacy budgeting, which are not specific at all to Jana, but are really kind of, I think, broader questions that the community is wrestling with. And in particular, I think that maybe one way to view this question of what kinds of values of epsilons should we be using. I mean, of course, it's application dependent. It's dependent on risk tolerance. But I think it's really quite similar to things like recommending key sizes in cryptography. You don't want to just ask one person. There's whole committees and processes and conferences and standard bodies that keep track of what we know and try to put things in context. So I think to expect any one project to sort of come up with the right and good answers is really not realistic. So our conclusions there is that it is expensive to generate the appropriately distributed noise for this secret sharing-based MPC, even for relatively straightforward mechanisms, and more work is also going to be needed on the policy side. So I do want to talk a little bit about application scenarios. These are slides borrowed, and this is the only place where I'm going to talk about kind of the structure of the Brandeis program. The way it works is different groups are partnered with each other, and so we've been working with the SRI team, and Karen Myers, who's the PI there, gave me some slides to use with her permission, which is about their work in building a platform. There's platforms all over the place. So theirs is a platform for doing kind of enterprise-wide information sharing and mediation, and we've been working with them to provide some of the security pieces for that, and so they have their own sort of picture of how they look at things, and privacy is a big piece of it. And then what it's really been helpful for is kind of driving application scenarios, and they've been looking at work with the US Pacific Fleet and Pacific Command around information sharing for coalitions in the Pacific. And they have this quote I love from a science advisor in the PACOM, that information sharing is one of our biggest challenges. So, so that sounds ripe for secure multi-party computation plus differential privacy. And in particular, some of the things that makes it a challenge for them really are about kind of the privacy and security issues. Of course, there's much more than that. And so we've been doing work with the SRI team, with our Jana team. There are other teams involved that I'm not going to really talk about, looking at scenarios that were developed in collaboration with this PACOM. So for example, humanitarian assistance and disaster relief. And so there's multiple different kind of problem areas within that that give rise to actual queries that you might be making around things like privacy-aware common operational pictures, what to do in a pandemic, and distributing aid to those who need it. And that leads to a way to run Jana on a particular data schema with some queries, and you get down to the much more specific. And so not going to interpret these at all, except with one exception, but to say that, so then they've actually taken our Jana platform and run it on these various kinds of queries, and it helps us, again, sort of understand where there are limitations, where things work well. One that I will point out is if you look at a query that is not, that is sort of very taxing for Jana, for speeds specifically, you get this very quick blow up, and it's pictures like it's curves like that lead to this push to consider things like order revealing encryption. And so this sort of helps us not just say, well, you just shouldn't use these less secure things. It's the efficiency penalty of not using them that leads to coming back to that over and over again. So to conclude, Jana is proving to be, I think, a useful platform for us in terms of exploring the feasibility, the scalability, the flexibility, the privacy, and the limits of these various tools and methods. It's definitely leading to some good research directions, as well as to just sort of solving the more operational challenges. And we'll continue to explore these trade-offs, and more work is needed. It's really work in progress, but it's been a lot of fun to work on. So.
Got time for maybe a quick question. Yeah, Ben?
So how are the parties communicating? Are they on LAN? Is it over the internet?
Right. So exactly what's done experimentally in those pictures, I'm not sure. It could be done various ways. I mean, definitely, we'd like it to be the case that the deployment scenario gets to have some say over who the secure computation parties should be, and certainly in things like a Pacific, if you're doing disaster relief and you've got these endpoints in turbulent areas that don't even have infrastructure, you'd have to, if you're getting input in and out from them, you might want to do something different than in a sort of, we're all sitting in a big enterprise somewhere.
It's kind of hard to judge you give running times, but you have a 10 gigabit LAN.
Yeah, absolutely. So certainly, if you delve into any of it, like if you look at the paper just on the different kinds of MPC-friendly secure encryption, they sort of take at least two scenarios, one to say a local area network, one a wide area network. But you're right that even to just answer questions about is computation the bottleneck or communication, it depends very heavily on the actual scenario, for sure.
Okay.
Great.
Let's take any remaining questions for the break, and thank Rebecca.